Hi, I'm Liz Olson,
And I'm Mason Preston.
representing our final project for microcontrollers. Our project is a plant environment monitor system. This system uses 4 sensors to observe the environment around a plant. These sensors include temperature, humidity, light, and soil moisture.
There are 2 outputs, 4 LEDs that display any out-of-bound environmental values and an LCD that displays the readouts of the values and also any warnings. The sensors communicate with I2C for the temperature, humidity, light, and use an ADC for the soil moisture.
I'm going to introduce the hardware that we used. So for the inputs, we had 4 sensors on 3 boards. 2 of them were on the same board. So that was the temperature and humidity sensor. This is the Adafruit High Precision Temperature and Humidity Sensor, or HDC 3022. We selected this because it was available in the ECE store. There were no satisfactory light sensors, and there were no soil moisture sensors available there, so the other 2 components were ordered online. The light sensor is the SparkFun Optical Sensor, or VEML6030. We selected this one based on the frequency of light that it could sense, since plants require certain frequencies or certain wavelengths of light, and this was able to detect those. We selected the soil moisture sensor. This is the Grove capacitive soil moisture sensor. We chose this over a resistive sensor because those are more prone to corrosion and do not last as long.
So for the structure of our software, first we initialize the peripherals, which are the I2C, the ADC, the PWM, and the LCD driver code. And then the rest of the function is handled by a looping state machine, and the states are changed by a SysTick interrupt. For the state machine, each state represents one of the 4 environmental values that we're monitoring, and the state is checked every 25 seconds when the state machine loops. Every time it loops, the data for all the values are updated, and the warning flags for all the values are updated as well. And these warning flags will automatically enable the correct warning LEDs as appropriate. The relevant data for the current state that the state machine is in is converted into a readable readout for the LCD, which is then printed to the LCD along with any relevant text warnings that we want to print as well. And the state is changed every 5 seconds using the SysTick interrupt, which uses HSI over 8 for the clock because otherwise it wouldn't be able to make a full 5-second delay. For the peripherals, we're using I2C for the communication with the light and temp sensors. The code for the I2C is pulled straight from the book, but is not fully used as it is for both of the sensors. The temperature and humidity sensor uses a fairly normal implementation of I2C, but the light sensor uses we call it a no-stop version, where in between the send of the command and the read of the data from the peripheral, it doesn't stop the communication line. We're using a 12-bit ADC to collect the analog data from the moisture sensor. This value gets displayed as it comes out of the ADC, so it's relative and also unitless, so it needs calibration and some knowledge of what exactly it's reading in order to be used properly. And we trigger this ADC with software at the same time we communicate with the other sensors with the I2C. The PWM, we're using 4 channels on timer 2, and each of the warning LEDs is connected to one of the channels on the PWM. We do this so that we can easily enable and disable the flashing LEDs by just using the channel enable bit, and the PWM is a low frequency PWM so that the LEDs flash at a reasonable speed. The LCD is connected in the same way it was for all the labs that involve the LCD, and is used for reading the data and the warnings as text.
Here is our microcontroller setup. So from left to right, we've got our soil moisture sensor. We've got our LCD that displays readings. It cycles between the sensors every 5 seconds and updates the readings every 25 milliseconds. That also displays warnings here. And over here we have our temperature and humidity sensor and our light sensor, then our LEDs. From left to right, they are soil moisture, humidity, light, and temperature. So as you can see right now, the soil moisture sensor and temperature sensor are going off. So if we look over here, you can see that I'll wait for it to cycle back. Here you can see the light reading changing. If I put my finger over the light sensor, it drops pretty quickly and the warning LED comes on. If I take my finger off, the warning LED goes off. As for the temperature sensor, you can see it over here. If I put my finger on it, it rises pretty quickly and the LED turns off. Take my finger off. It takes some time to attenuate, but it will turn back on. Here you can see, once again, the soil moisture sensor is going off, so it means the soil over here is too dry. So then I will water our plant. And after the water sinks in to the soil, I'll move the sensor over to the wet soil. The light will go off. One of the biggest challenges we faced in this project was the I2C. First, our biggest issue was managing the GPIO pins. Originally, we wanted to use I2C2, which used GPIO-B pins 10 and 11, but we had to use those for our PWM, so we ended up switching to I2C1. We made this change in hardware, but we did not make the change in software. Spent a lot of time trying to figure out what was wrong, and it ended up just being configuration. We also realized that our pull-up resistors were too small. We had to change them based on some documentation for one of the sensors. We also found that we had to shift the addresses for the peripherals by 1 bit to the left, which was not in the postcode. We also had to implement a no-stop version of the I2C for the light sensor, since it doesn't have a stop bit between the send read command and actually reading the data.
Another issue we faced was with the LCD implementation. Because we had already disassembled our hardware for the LCD that we used in the labs, when we reassembled it, 2 of the wires got swapped incorrectly and burnt out part of the backlight. So we had to use a different LCD. Additionally, in our final code for this project, we were using the 16 megahertz clock, HSI clock, and our LCD driver code was written based on a 4 megahertz clock. So some of the delays in the commands were too short, and there were some places that needed additional delays that didn't need them previously. Additionally, the display string function would access data it wasn't supposed to, so we had to make sure that all of our data readouts and warning readouts were exactly 16 characters.
Another issue we faced was with the PWM. As mentioned earlier, there were some conflicts with the GPIO pins where we wanted to use GPIO A, 2, and 3, but those are reserved for USART for the ST-Link debugger. So we ended up having to use GPIO-B pins 10 and 11 for those 2 LEDs.
We faced a minor issue implementing the ADC, which was simply configuration error. The input channel was just not set properly.
In conclusion, our final project is a plant environment monitor that displays readings and warnings from a set of 4 sensors for temperature, humidity, light, and soil moisture.
For these sensors, we used I2C as a communication protocol between the sensors and the microcontroller, and an ADC to convert the analog data from one of the sensors.
We then took this data and displayed it on an LCD and set thresholds to trigger warnings that also displayed on an LCD, and started flashing a set of LEDs. To do this, we used a state machine to cycle through each reading.